and welcome to episode number 7 of CS350 Online. I'm your host, as always, Leslie Eistedt. In today's episode, we are going to continue our discussion of semaphores, looking at some interesting places where we can use them. We're also going to take a closer look at the implementation of the semaphore, in particular, the ordering of those two lines of code between wChainLock and SpinLock release, and hopefully that will help clear you up on why those two lovely little functions calls have to be in that particular order. What else are we going to do today? We are also going to talk about condition variables, and hopefully that will get you into the right spot so that you can get going on assignment 2. Now, I know if assignment 1 hasn't been submitted yet, but you know, it's always good to have a good idea as to what they are. All right, so the readings, if you are following along with the textbook, are posted on the screen there. And again, the textbook reading is not required. It's kind of considered extra. I do think it's a really good book to read. It's got some wonderful resources, some little code snippets which are actually quite useful, but it's really up to you. We're not going to ask you any questions on the quizzes or on the final assessment about things that come directly from the textbook. Everything that is on a quiz or on the final assessment is either directly from the course notes or it's going to be something that we spoke about in these episodes. The other thing I wanted to remind you of is with assignment 1, no matter how tempted you are to use pthread join for this or that reason, please don't use it. We really want you to use other mechanisms in this assignment. The other thing I will say is, yes, I'm aware that without using pthread join, you are going to have a tiny little memory issue. And again, we're not running Valgrind, so don't worry about it. Okay? It's not a big deal. It's not CS136. It's 350. All right. So what we have today for our OS of the day is called, we talked about DTSS, didn't we? That's the wrong one. We talked about CTSS, which must mean we are on to the wonderful world of Multics. Yay. So Multics was developed / released in 1969, and it was actually released for several machines, including the GE645 and the Honeywell 6180 series machines. Again, remember how last time I said that all of those companies that you associate with things like your heating and your electrical and your thermostats, they actually used to make mainframe computers a really long time ago. And this operating system is actually out of MIT. So there's a quick question on Twitch to address. Do we have a quiz schedule yet? So if you follow the episode guide, which is kind of rough, they follow the course modules, and there's one per course module. So, I mean, it's kind of up to you when you do them. I wouldn't recommend saving them to the end, though. I can tell that. All right. So what does Multics stand for? So it stands for Multiplexed Information and Computing Service. And you can start to see, hey, we have a logo for this OS. Yay, that's kind of fun. And this logo actually kind of has a meaning to it. So this is a very important OS in OS history because this is the direct predecessor of the Unix operating system, which we'll obviously be talking about very soon. But because it is the direct predecessor of Unix, you can imagine that it has lots of interesting functionalities and features that we might be interested in. So first off, they offered single-level storage. So there's no separation between the file space and the address space. So you could see all memory from the file system. And that's a big difference from how memory has been treated in the past. And it has some really interesting side effects, as you might imagine. Because now you've almost abstracted how memory is accessed into a single common system. Kind of cool. You also have this concept of dynamic linking, so you can include and access data from other programs outside of your own address space. And you can use that to include in your own data. And this is something we use all the time, right? So for example, if you're on like Windows, or if you're on a Unix-based operating system, and you're trying to write a program with OpenGL, you do not have to actually physically include all of the OpenGLs statically in your code. You can dynamically link against them under the assumption that whatever computer you're actually running on will actually have those libraries already there. Now, obviously, that does introduce some problems with versioning and so on and so forth, but generally speaking, that's the idea of how that works. Now, here's one of the very odd ideas they had was they wanted you to be able to reconfigure the hardware while the operating system was still running. So without rebooting, they wanted you to be able to like pull 500 kilobytes of memory out and the OS would keep going. Or if you had two CPUs installed, they wanted you to be able to separate a CPU and off and then it would still work, or add things. Now, as we all know, some of those, you can't do that in a desktop today. I can tell you this from personal experience. Don't reach into your desktop computer and pull your network card out while the computer is still on and running. You will get a shock. I'm telling you this from experience. Yes, I did it once. It's not a fun shock either. I mean, no shock is fun, but I want to say it was worse than an electric fence. I'm going to guess you probably have never touched an electric fence. Don't do it. I don't recommend it. I mean, it's not that bad, but don't do it. And also, please don't pull cards out of your computer while it's on. That's a really bad idea too. So, but if you're talking about these big mainframes, you're not talking about like reaching into the computer and like pulling out a board. They're bigger components and they're often designed in such a way that they have like handles that you can actually pull pieces out on. So it's kind of meant to do this. But the idea was that the operating system could keep running even while you're reconfiguring the hardware. And that's a really interesting idea. And I don't know how successful they were in this. I don't imagine it was overly successful simply because it's pretty complicated to implement something like that. But considering they were not running on generic hardware, maybe it did work for them. Obviously, Multics is still kind of around. I don't think it's under active development anymore, but it has since run on varying hardware, so the support for that, I imagine, has changed a fair bit. Now, some other interesting things is they decided that there should be different levels of security. So there should be something like a kernel should have a certain amount of access rights, and the user should have a certain amount of access rights that are different from the administrator, simply because I don't want my user to be able to dive into another user's address space and start taking data. That's really bad. So they developed this concept of rings of security, and depending on which ring you were in, depending on what kind of access rights you had to various things in the kernel and outside the kernel. They also had a hierarchical file system with symbolic links. They did per process stacks within the kernel, which is fairly new. And they also had command processor and as a user application. I mean, we could go on about Multics for a long time because it is a very important OS and it is Unix's predecessor. But that's all we're going to say today. And you can actually still get your hands on this operating system if you want to play with it in a virtual machine. That's kind of fun. Admittedly, the only virtual machine that I actually keep around. So I guess I have DOSBox, just kind of a VM. But if I'm going to keep a virtual machine lying around my house, I usually keep Windows 3.1. Because I like to play Windows 3.1 games in their native environment. All right. So where did we leave off last day? I know it was like 5 days ago and hopefully got out and enjoyed the weekend. So let's go back to where we were. This is not where we were. This is called my kids were playing on my computer. Okay. So we left off, we talked about how to implement locks. And we talked about the differences between a lock and a spin lock. So remember, both of them are going to offer us mutual exclusion. But the big difference between a lock and a spin lock is a spin lock, when the lock is not available, you're going to be busy waiting. So you're going to do that active executing code on the CPU to check whether you are available or not. Whereas a lock, or a lock that blocks, when the lock is not available, instead of sitting there knocking on the door repeatedly, we're actually going to go to sleep. And when we're asleep, we're not in the ready pool because we cannot execute anything because our resource is not available, and we're not running either, so we're not wasting the CPU's time. And then what happens is that the thread that releases the lock is responsible for waking us up and putting us into the ready pool so that we actually get a chance to run. And the place that we wait is called a wait queue or wait channel, and those are already implemented for you in OS 161. There are the following 4 API functions that you will need to use throughout assignment 2. So there's sleep, which is going to put the current thread to sleep and cause a context switch. There's wake all, which wakes every thread that's waiting on the wait channel. Wake one wakes one thread. And then there's lock, which we have to use in conjunction with sleep in order to provide mutual exclusion while we are actually doing the context switch and putting a thread to sleep. Then, so we went over the implementation of a lock, and if you missed that episode, obviously you can go back and look at it, or if you're on Piazza in the extra sample problems thread, we have the pseudocode for acquire there as well. The other place where you can actually find some starter code for locks is actually in Semaphores, which are implemented. All right. So how is a semaphore then different from a lock? So a semaphore has a counter. Instead of having the concept of this is a locking door, the door is either open or shut, a semaphore is a bunch of chairs in a room. You have a fixed number of resources, and you can enter the critical section so long as there are resources available, and if there's no resources, then you cannot enter the critical section and you have to go to sleep. So a semaphore is usually used for those cases where you have a number of resources that you want to keep track of. Whereas a lock can only let one person into the critical section at a time. Now, because of the inventor of the semaphore, the functions for acquiring and releasing a semaphore are called P and V, not acquire and release. This takes some time to get used to, but remember P is for acquiring. So we P a semaphore to try to acquire it, and we V a semaphore to try to release it. We also talked about 3 different kinds of semaphores, and they all have the exact same implementation. This isn't 3 separate implementations. It's the same implementation used in 3 very different ways. So there's the binary semaphore, which is giving us mutual exclusion, so it behaves like a lock. It's a semaphore that starts with a singular resource, and we never increment it beyond that. So we'll always P before we enter the critical section, and we only V when we leave the critical section. Now, this behaves just like a lock with a few little exceptions, one of them being that if you use it incorrectly, it will lose that mutual exclusion behavior. The other thing being that the semaphore does not keep track of ownership, so anybody could technically release it. Binary semaphores are actually very useful, though, especially when it comes to working with devices and device drivers, because there's never a guarantee that the thread which acquired or initiated the contact with the device is going to be the same thread that picks up the interrupt from the device. And if we oftentimes, not always, but oftentimes, it doesn't matter who releases the device, it's just that it gets released. So binary semaphores are really, really useful for device drivers. Counting semaphores we see used in many, many places, especially when we're keeping track of the number of resources available. And then the barrier semaphore is just our implementation of join, effectively. So what we do is we start with a semaphore that has no resources, and then the thread that is going to fork or needs to wait for all the other threads is going to P the semaphore once for each thread it needs to wait for, and then as the threads that it's waiting for finish, they're going to V. So you are blocking, the semaphore is blocking the calling thread from moving on until all of those other threads would have actually completed. So those are 3 simple use cases for the same implementation. Now, one of the interesting things to keep, 2 interesting things about a semaphore. Number 1, you should never access the counter of a semaphore directly. That is outside of P and V, and the reason is because it's a shared variable, and if you try to access it directly, whether it's reading or writing, then you're going to run into a race condition, and that would be really bad. The other thing is that our implementation of semaphores doesn't keep track of the maximum number of resources. So if you're like, well, I could fix the binary semaphore implementation by just saying the max resources is 1, that's not how our implementation works. We have a singular counter. Okay. It's not to say you couldn't implement something like that. It's just that's not how ours are. All right. We showed you briefly how to use a semaphore for mutual exclusion and barrier. And that leaves us today with talking about a very common place that we actually use semaphores. And that is in the famous synchronization problem, producers and consumers. Now, for those of you who are sitting there trying to plan out the rest of your third and fourth years, there's another course I could highly recommend that you take, and that is CS343, or the concurrency course. It actually used to be called CS342, and it used to be the prerequisite of this course. Or was it 342? I don't remember. It was a long time ago. Yes, it was 342, because this one used to be 354. Eons ago. Now, why would I recommend that you actually take this concurrency course? Because I know concurrency is not a required course for BCS degrees. The reason is that in today's landscape, multi-threading and concurrency is everywhere. It's in web programming, it's in low-level programming, it's in game programming, it's in graphics, it's in film, it's pretty much everywhere. And the reason, of course, is that now that we have hardware that actually supports multiple threads running in parallel, it would be really nice to actually take advantage of that. And so people are more and more often looking at, how do I make multi-threaded solutions to improve the performance of this particular problem? How do I make it so that the program gives me more immediate feedback? And so multi-threads comes into play, concurrency comes into play. So in terms of if you're going into industry, pretty much no matter where you go, I want to say getting a greater understanding of concurrency is actually a really good idea. And Peter Brewer usually teaches it, and he's awesome. But yeah, I recommend you take concurrency. And in concurrency, you will learn about many famous concurrency problems, like the barbershop problem and the dining philosopher's problem, and of course, a more basic one known as the producers and consumers problem. So the producers and consumers problem is a fairly simple problem. So I like to use a car manufacturer as an example here. It's particularly relevant to me today because I think I need to flatbed my car to my mechanic. And hopefully my engine can be fixed. If not, I might have to buy a new car. If you're sitting out there thinking to yourself, I'm going to buy a nice rally car and I'm going to mod my engine, just don't. Just don't. It's fun to mod your car and make it go faster and have more torque and more horsepower, but you're also signing yourself up for a lifetime of expensive engine problems. All right, so let's pretend we are the Subaru plant in Indianapolis, which I actually believe is still shut down right now. So they're a car plant, and outside of the plant, yes, I've been by it, road trips, you know, there is a big parking lot, and the parking lot has a fixed number of spaces. And the parking lot is where all of the brand new cars that were just built are going to sit until the dealerships can send trucks to take the cars away. So the parking lot is what we would call a bounded buffer. There are a fixed number of places. So here's the problem from the perspective of the Subaru plant. There are only so many spots for them to put new cars. So if they're building cars and there's no free spots to put the cars, then where do you put them? Well, let's just say you throw them out. So they can only build a new car if there's actually a place in the lot in which to put it. And the other side of the problem is the dealership problem. The dealership wants to come and get cars from the plant, but there's no point in sending a truck from Nunavut down to Indianapolis if there's no actual cars waiting in the lot. So we actually need to synchronize this problem. We need to make sure that the plant doesn't produce any cars if there's nowhere to put them. And we also need to make sure that the dealerships are not sending transports to pick up cars if there's none available, because this would be a waste of time and money and resources and all these things. If you didn't guess, yes, I have a Subaru. It's an STI, 2010. All right. So how are we going to solve this problem? And the answer is we can actually use semaphores. Now, how many semaphores are we going to need? Well, what are the resources? When we're thinking about semaphores, we think about what are the resources. Each semaphore should track one and only one type of resource. So there's two resources here. The resource for the plant is the number of empty spaces in the parking lot. So it needs to know how many spaces are there. Whereas the resource for the dealership isn't how many spaces are in the lot. It's how many cars are in the lot. Now, this is where a lot of people ask, why can't we just have one semaphore and we access the counter? You can't access the counter because that's going to cause a race condition. So we need one semaphore to keep track of the spaces and one semaphore to keep track of how many cars there are. And this is how we can solve the synchronization issue between the dealership and the car plant over this bounded buffer. So we create two semaphores, one for the items or the cars in the buffer, and one for the spaces in the buffer. So we start out the day with nothing in the parking lot. So there's no cars. It's completely empty. So we create the semaphore with 0 resources. And then since the lot is empty, that would mean that there are n spaces. So it's completely open. So what the producer is going to do, that's the plant, is it wants a space to put their new car. So it P's spaces. When there is a space available, it will add the car to the parking lot. It adds the item to the buffer. And because it added an item to the buffer, it created a resource for the dealership. It created a car. And so now the number of items in the buffer is not 0, so we need to increment those resources, so we V items. And similarly, the consumer is going to be waiting for an item in the buffer. And when there is an item, it's going to remove it from the buffer. And when it removes it from the buffer, it is effectively creating an item that is a space for the other semaphore. So we are going to create the resource for that. Now, this code actually still has a race condition. The problem that we actually still have with this code is that the buffer itself is a shared resource, and it's entirely possible that someone is trying to put a car in the lot at the same time as somebody removing it. And that means that we have two threads or more threads trying to access the buffer at the same time. And that would be very bad. We can get all kinds of different race conditions. So we actually need to introduce either a binary semaphore so that we're guaranteeing mutual exclusion on the buffer itself, or we would use a lock to guarantee mutual exclusion because we only want one person in the buffer at a time. Otherwise, we're going to get race condition. All right. So what does the code for a semaphore look like? As I said, it looks almost identical to a lock. It has a few extra little fiddly details that a lock doesn't need, but this is the general gist of things as taken from the OS 161 source code. And you'll see it has the same format that the lock code has, but the exception, of course, is we're dealing with a counter and there's no ownership here. Okay. So you'll notice again that we lock the wait channel before we release the spin lock, and we use this spin lock to protect the test and set operation where we're testing the counter and then setting it if we are allowed to. We're doing a spin lock here instead of assembly because nobody wants to do inline assembly for this. All right. And then in the V or release operation, we acquire the spin lock again because we are going to be changing those shared variables. So we want to make sure we have mutual exclusion. We increment the counter, we wake a thread, and then we release the spin lock. So why does a lock have to be before the spin lock release? Why do these two lines have to be in this specific order? Let's actually go over this. So let's assume that they are in the wrong order. That is, we spin lock release before we lock the wait channel. Okay. So let's suppose that there is a semaphore and it currently has no resources available, and a thread is trying to acquire a resource at the same time as a thread is trying to produce a resource. So we have a P and a V happening at the same time. So if we spin lock release before we lock the wait channel, this is what's going to happen. So we'll spin lock release, and that could cause us to have a context switch. A context switch could happen right afterward. During the context switch, thread 2 gets to execute V. So we're going to increment the count. We acquire the spin lock, increment the count, wake a thread, but nobody's waiting yet because we haven't gone to sleep yet. And then we release the spin lock and we context switch back to thread 1. Now thread 1 now says, okay, I need to go to sleep on the semaphore because it is under the belief that the that the semaphore still has no resources. And so it calls lock and then it calls sleep. But here's where the problem comes up. Thread 1 is now asleep on a semaphore that actually has a resource. And who is going to wake it up? If there are no other threads that call V, then this thread 1 will be asleep on the semaphore forever. So if we have spin lock, release, and lock, W-channel lock in the wrong order, we can actually fall asleep on a resource that's technically available and we may never wake again. And that's very, very bad. Now, in comparison, when they are in the correct order, let me tell you what happens. Let's suppose you lock the wait channel and then we call spin lock release. Then there's a context switch to thread 2. Thread 2 calls V. It acquires the spin lock. It increments the count. But when it calls wake 1, instead of returning from wake 1, it causes a context switch immediately. It's not going to work because the lock on the wait channel is owned by thread 1, which means that thread 2 cannot do any wait channel operations at all. So we're going to have a context switch back to thread 1 where it can finish off with the wait channel, actually put the thread to sleep, release the lock on the wait channel, and then there would be a context switch in sleep, and at which point thread 2 would wake up inside of WChan wake 1. It would then wake you up and then release the spin lock, and then you would wake up and you would recheck to the resource availability. So when these are in the right order, when these two are in this order, you are preventing threads from falling asleep on resources that are available. You are guaranteeing that if a thread falls asleep on a wait channel, it is because there is no resource available. Okay? It's very important those two lines go in the correct order. If they are in the wrong order, very bad things happen. And I showed you this for semaphores, but the exact same situation happens with the lock. And it's absolutely critical these lines are in the right order. And I believe the lock guide goes over this again, except for locks. So if you're still struggling to see why this must be, trace through it a few more times. You'll see some really funny behavior happens. All right. So then, what next? Well, now is the time to talk about our last synchronization primitive. And if you're sitting there thinking, oh, so we only have locks, semaphores, and condition variables. Those are the only synchronization primitives out there. Oh, no. There's lots more. There are monitors. There are all kinds of other ones. There's lots of really interesting synchronization primitives. And that's a good reason to take 343 because you'll learn a bunch of them, right? And you'll get to play with them. Along with a lot of preprocessor stuff. So the last one we're going to talk about is the condition variable. And this one's kind of odd in comparison to the other two, in the sense that it has to actually be used in conjunction with the lock. So you cannot use a condition variable on its own. It has to be used with a lock. And let me describe the problem that a condition variable is trying to solve. So a condition variable is meant to be used where you are in a critical section and you reach a line that has mutual exclusion, and you reach a line of code where you need a shared variable to have a particular value. But it doesn't have that value. And here's the problem. You can't continue if the shared variable doesn't have the right value. But because you have the lock that protects that shared variable, nobody else can change it for you. So you're kind of stuck. So the idea here is that what we want to do is we want to be able to safely fall asleep and release the lock. Because we're asleep, it's fine to release the lock, such that the other thread has an opportunity to change it and then wake us back up and we can continue on our merry way. Another way to think about this, and I know this is going to be a foreign concept because in the last 2 years, no one's actually been able to go to a bar. I can't even remember the last time. I used to go to Morty's for wings, but now I just do curbside pickup from there. Anyways, let's suppose, remember in that long, long time ago, that you were at a bar and you have a, well, this is cranberry juice, but let's suppose that you've got, a pint of beer in your hand. And because the beer is in your hand, you have the lock on it. So you take the beer up to your mouth and you realize, oh, it's empty. You're like, oh. Well, I guess I can't take a drink then. But here's the problem. Because you have the ownership of the critical section, you have mutual exclusion on the cup, the bartender can't actually refill your cup. Because they don't want to reach over the counter and try to pour it in from the keg into your cup because you're probably all shaky and stuff, So what has to happen, what a condition variable lets us do, is we're going to simultaneously put the cup down and fall asleep. We are asleep, which means we are not trying to access the cup. We can't. We're not executing any instructions. So there's not going to be any race conditions caused from that. But that, by falling asleep and letting go of the cup, we've now given the opportunity for the bartender to come, pick up the cup, refill it. When they pick up the cup to refill it, they're, of course, acquiring the lock. They change the value. And when they release it, they're going to signal to us that the cup is filled. And you might imagine they might, tap you on the shoulder or throw the cup down the bar top and it smacks you in the head. And when it smacks you in the head, you are going to simultaneously pick up the cup and wake up at the same time. So when you wake up and you go back to executing, you have the lock on the cup. So when you fell asleep, you had the lock on the cup. And when you wake up, you have the lock on the cup. So while you were asleep, it was okay for other people to touch it. And that's what the condition variable and lock pair is going to let us do. It's kind of fun. Now, there are 3 API functions for a condition variable. And again, this is, by the way, you have to implement these. You get to implement locks and you have to implement condition variables. And the prototypes are all there. You just got to fill it in. So the 3 functions that we have are wait. Wait is where the bulk of the code goes. And it is going to have the code to simultaneously fall asleep and release the lock, and then just before wait returns, it's also going to have the code to simultaneously wake up and acquire the lock. So all of that work actually happens inside the CV wait function, away from whatever it was you were doing, so you can be guaranteed there's no race conditions over the shared variable. So that's kind of cool. Signal and broadcast are the notification functions. So signal is going to notify one thread that the condition has changed. So we're going to wake one thread up. And then broadcast is going to wake everybody up. Be careful when you use these two. If it's only ever possible for one thread to use the condition at a time, then you probably just want to use signal. Whereas if every thread can do it, then it is okay to use broadcast. You don't use broadcast if only one thread could ever be successful, simply because, you wake 1,000 threads up and only one of them can be successful. Then you have to waste all that CPU cycles putting 999 of them back to sleep again. So be careful about using these. Okay. Now, we can actually use condition variables to solve the producers and consumers problem as well. We just have to change our frame of mind. Instead of thinking about things in terms of resources, now we need to think about things in terms of what are the conditions we're waiting on. So the condition for the producer is that the number of items in the buffer is less than n. So the number of cars in the lot is less than n. And the condition for the dealerships, the consumers, is that the number of items in the buffer is greater than 0. So we can take the same problem and rethink it. Instead of thinking of resources, thinking about conditions, and we can just solve it differently. And by the way, this is actually a really common thing that you would actually see people do with synchronization problems is we've solved problem X using locks. Now go solve it using semaphores. Go solve it using condition variables. They can be used to solve all of the other problems. But it's just which one makes the most sense, which one is the least code. So I'm going to... Before we get into solving the producers and consumers problem, I want to show you kind of where the use for condition variables comes from, and then how do we actually use them. But before that, there is a question on Twitch. Is one way better or preferred than the other? So here's the question you have to ask. If I'm trying to solve a synchronization problem, and the problem is something, it boils down to producers and consumers, and you see that as being a problem of resources, then you should use semaphores. Semaphores are a very simple way to represent the solution to that problem. Like, it's a very understandable way. Whereas if you try to solve producers and consumers with just locks, it's possible and it will work just fine, but the solution isn't as elegant. And there are places where solutions are not as elegant if you use semaphores than locks, although admittedly, semaphores are actually very versatile, so I tend to use them everywhere. But sometimes a problem will be more easily phrased with one of them than the other. And is there a magic instruction I can give you to tell you which one is most appropriate for the problem? Not really, because sometimes people will see a problem as a problem of conditions, and another person may see it as a problem of resources. So there's no real magic way to say, use these here, use these there. I mean, I can say semaphores if you are trying to have mutual exclusion, but ownership is not guaranteed. Like, ownership doesn't matter, then semaphores are good for that, whereas locks aren't good for that. But again, this is tricky. Is there a performance difference? That's the next question on Twitch. Yes, there can be. Not all of the solutions would be created equal. For example, we're going to solve this condition variable problem here, and you'll see that the condition variable example is a bit better than the other one. So it's not to say that this is always the case. Sometimes it is the case that performance is better with one than the other. It depends, again, on how you phrase the problem with it. So here's the little app that I'm creating. And again, this is an app that, since you're not on campus, it probably doesn't have any meaning. But as you know, in the springtime, there are lots of geese on campus. I mean, they're on campus all the time. But in the springtime, everyone says that they're super aggressive because it's, mating season and all that. So somebody might want to make an app where you put your path in, and then you can only continue to walk from your home to your class if it is safe to walk. And it's only safe to walk if the number of geese on your path is 0. So let's actually try to solve this. So we have safe to walk, this is our function, and we have a geese mutex, which is going to protect the number of geese. And again, we will come back and talk about this volatile word here. We're not going to talk about it right now. So don't just pretend it's not there for now. But let's say we have 100 geese right now. So we acquired the geese lock because we want to check how many geese there are. And we can only continue on to to say this is safe to walk and continue on our way if the number of geese is equal to 0. So if the number of geese is greater than 0, we need to wait. But here's the problem. If I wait here for the number of geese to change, I also need to release this lock. Yeah, but how do I do that safely? How do I safely pause and release the lock at the same time? So let's actually just try to solve this with locks. We can, by the way. It's not that bad. So here's what we're going to do. We're going to introduce a while loop. So we're going to say so first thing we're going to do, we acquire the geese mutex, and then we're going to say while the number of geese is not equal to 0, so while there is more than 0 geese, we are going to release the lock and then acquire the lock again. Now, why do we do that? Well, we do that because we want to encourage a context switch. So we release it, and there could be a context switch then between these two functions, which could cause another function to acquire the geese mutex, change the number of geese, and then when it releases it, we are going to get an opportunity to acquire the lock again, and then try this whole thing again. And we're going to loop. This is a busy wait, waiting for the number of geese to change. But this technically solves the problem. Now, if we wanted to encourage a context switch between these two lines of code, we could actually use a thread yield. This is one of the rare cases where thread yields are actually pretty useful. So if we put a thread yield in here in between these two lines, we'd actually encourage that. So this works. This solves the problem. We won't proceed in this safe to walk function until the number of geese is actually equal to 0. But in terms of efficiency or performance, this is really awful because this is a busy wait. We're busy waiting here. The majority of the time, we are going to be spinning, releasing, and reacquiring this lock. That's not good. We can do better, or we want to do better than this. I mean, technically, this works just fine. It's just, you could do better. So this is what we do to use a condition variable. So our condition we are waiting on is 0 geese. Now, one thing that's kind of odd about condition variables is they don't actually keep track of the condition itself. So a condition variable has no idea what the condition is. It's just a wait. It's just a holding ground. It's just a wait chamber. That's all it is. So our condition variable doesn't know what the condition actually is. You keep track of the condition, and then you call the appropriate CV API function. This looks almost identical as before, but the behavior is very, very different. So here's what we do. We say lock acquire geese mutex. Then we're going to say while the number of geese is greater than 0, call CV wait. Now you might be like, well, but we're still busy waiting. But you're not. Because when you call CV wait, you're going to go to sleep, which means you're blocked. And you are going to release the lock at the same time. And that means that somebody else can acquire the lock and change the condition. And when they change the condition, they will call signal. Signal will wake you up. But you will only call signal if we've set the number of geese to 0. So if we set the geese to 99 or 101, we're not going to wake you back up again because that's not what you're waiting on. When the condition is met, then we call signal to wake you up. So you do not sit here spinning actively. You're asleep, and you stay asleep until somebody actually wakes you up because the condition is now met. Why do you still need the loop, though? Unless we are doing what's known as an explicit handoff, which this is not. We are going from asleep to the back of the ready queue. Means we're not going straight from sleeping to running, which means other threads ahead of us might get a chance to change the shared variable on us. So we need to check. The only time where we don't have to loop is when we have set the condition such that the only thread that could continue on is you, and no other thread that might run ahead of you could change it. So in the old traffic simulation problem, what we would do is the best solution was to have a traffic light. And to do the explicit handoff and prevent the while loop, what you would do is when the intersection emptied of cars coming from the north, you set the traffic light before you wake anybody up to the next direction you want to go. So let's say you wanted south to go next. So that way, any threads that show up that don't have cars from the south, even if they were ahead of you in line, they would have to wait. So only south cars. So that would let you actually do a handoff, whereas here we don't have that ability. So a couple questions on Twitch. First one is, in our case, CV is just a condition variable without any information. That's right. And that's a pretty standard implementation. Because how are you going to pass the condition exactly into the condition variable? You'd have to have some kind of like, I mean, I'm not saying you couldn't do it. You could absolutely do it with like a function pointer. Kind of like, how they've generalized the sort functionality. But it's actually just easier because it's your code. It's a lot easier for them to just say, okay, you manage the condition, and then you just call wait and signal when it's appropriate. So that's very standard implementation. Another question is, where do you specify the condition, which is number of geese equals 0? So that would be in a separate function. So this function, safe to walk, this is we're checking whether the number of geese is 0. Now, and that condition right here is this one here. We don't set the number of geese to 0. We're checking it. There's a separate function that would be setting it, and it would be, like a search function or something, and it would be like, oh, I see there's no geese, therefore set number of geese to 0. Oh, number of geese is 0? I better call CV signal and wake up anybody waiting. So that usually happens in another function somewhere else. So you'll be checking the condition in one place and often setting it in another. Okay? All right. So a condition variable, as I said, is just a fancy holding ground for threads that are waiting on a condition to be true, which means that a condition variable obviously needs a wait channel. There's a lot of temptation I've seen in implementations in the past for students to put the threads waiting on a condition variable asleep on the lock. Please don't do that. Threads that are asleep on the lock are waiting for the lock. Threads that are asleep on the condition variable are waiting for the condition to be true. We do not want to put threads that are waiting on different resources asleep on the same wait channel, because then we'd have to check what they were waiting on to wake them up, and that doesn't make any sense. So it's really nice if everything on a wait channel is waiting for the exact same thing to be true. Makes life easy, right? Now, just a note, if you are Googling for condition variables, they go by many names, and there are many different types. We've shown you a type of condition variables called Mesa style, and it's probably the most popular style of condition variable, to be honest. But there is another style you might find called the where style, where semantics, and they're very different. So with our kind of condition variables, when you wake a thread, it goes from the blocked pool to the ready pool. And the thread that woke you will continue going until it context switches out or whatever. That's the Mesa style semantics. The where style semantics is very, very different. What they do is when you call signal, you actually go to sleep. So you relinquish the CPU to the thread you just woke. Where these are very interesting to use would be real-time operating systems. We want to guarantee a certain response time for a condition being met. So for example, if the condition is there's nobody in the street in front of me, I'd probably want to respond to that right away and not wait for my thread to be scheduled and wait for me to finish. So when you want to respond to those events much more quickly, rapidly, that's when the where style makes more sense. But Mesa style is what most people use. It's what most operating systems would have. Where style is not that common, I find. I can't actually think of the last time I used a where style one. Yeah. Maybe it's CS350, but I don't remember because that was about 15 years ago. All right. So now let's actually look at the bounded buffer problem. So again, this is producers, consumers, but instead of doing it with a semaphore, let's do it with condition variables. Now, we need a lock. We only need one lock. Multiple condition variables can use the same lock. Why? Because there may be different threads waiting for the same shared variable to have different values. We still only need one lock to protect the shared variable, but we may need multiple condition variables in order to keep track of all the different conditions threads could be waiting on. For example, with producers consumers, one lock to protect the counter, two condition variables. One for the condition that the buffer is not empty, and one for the condition that the buffer is not full. So, there you go. And if we were doing traffic simulation, which we aren't anymore, there would be one lock and four condition variables. All right, so we've got one condition variable for when the buffer is not full. So that is the count is less than n. And we have one for not empty, so the count is greater than 0. Now, the code is a little bit longer here because it's a little bit longer. Sometimes it takes a bit more code to solve the problems with different synchronization primitives. So we acquire the mutex for the counter, and we're going to check, is the counter in the producer equal to n? Because if it is, then there's no free spaces. So we are going to call CV wait. We are waiting for the buffer to be not full, so we're going to call wait on not full. When that becomes not full, when we wake up and the count is less than n, we can add our item to the buffer, protected, of course, by this lock. And then we increment the counter because we've added a car to the buffer, which means that we've changed the condition for the consumer. So we signal the consumer to say that the buffer is now not empty. And then we release our lock. And then in the consumer, it acquires the lock, and it is waiting for the buffer to be not empty. So while the count is 0, it waits for the buffer to be not empty. So this is where we would wake up. If we had just signaled that the buffer was not empty, we'd wake up right here. And we realize, oh, the buffer is not empty. Okay, I can then take an item from the buffer, again, protected by this lock. And then after I take it, I decrement the number of items in the buffer because I just took one, which means I just changed the condition for the producers. So I signal the producer to let them know that the buffer is now not full, and then I release the lock and return the item. So producers and consumers can be solved with semaphores, or it can be solved with locks and condition variables. Kind of neat, right? Same problem can be solved different ways. And it's up to you to decide which one is more efficient. From a coding perspective, I'm going to tell you right now, for producers and consumers, I'm going to choose the semaphores. So question on Twitch is, how does another thread know when to signal and wake me up when I don't provide any of the info for the condition? Well, it's up to you to tell it. So here we change. See this line right here? We are removing an item from the buffer. So we've decremented the count. Because I decremented the count, I now know as the programmer that the number of items in the buffer is not equal to n, which means I know that it would be possible for the producer to go. So that is why I call CV signal here. So it's up to the programmer to keep track of when the condition changes such that they could actually wake up the other threads. Okay, so it's on you to manage the condition. Okay, again, the CV is just a fancy place for threads to wait. Okay, so another question is, if there are multiple condition variables, does each condition variable get its own wait channel? Yes, because each condition variable should be for a different condition. So for example, in this producers and consumers, I have two condition variables. The threads waiting on not full are waiting for the buffer to be not full. The threads waiting on not empty, on the other hand, are waiting for the buffer to be not empty. So each condition variable does have its own wait channel because the condition for each condition variable should be different. Okay. So the next question is, doesn't CV wait block the current thread? How will we execute lines below the while loop? Well, if we block, we have a context switch. And that means that another thread will get to go. So in this particular case here, when we call CV wait, we're going to have a context switch, which would let the producer go. And the producer could go because the count of items in the buffer is, equal to 0, which means that the producer could safely run because there's spaces in the buffer. So here, by waiting, we are giving an opportunity for the producer to run and change the condition, and then they signal us to wake back up. So, yeah. Once we wake back up, and inside of CV wait, we will wake back up, then we would continue on our merry way. Now, if you're sitting there wondering, how do we implement condition variables? Because it is part of assignment 2. So part 1 of assignment 2 is to implement locks and condition variables. We've already gone over the lock implementation. I would like to show you some rough thoughts on the condition variable implementation. The reason why I'm doing this is because you need them. And when we haven't given you any hints about the condition variables, I've seen all kinds of really bizarre things. And to be honest, if I have to answer the same question 20 times in office hours, I'd rather just post it in the episode. This saves time for everybody, right? So, maybe OneNote's working better today. It updated, so wishful thinking. So not gonna happen. Oh, my computer's really mad at me. These MacBooks, what happens is when the CPU temperature gets to a certain point, they actually throttle the CPU down by reducing the voltage to try to decrease the heat. But the problem is when you turn the voltage down, you're also turning the performance down a lot. And the computer I intend to buy is still not released yet. I really don't want to buy the 17-inch model because carting around a 17-inch laptop is not fun. Well, maybe it is for you, but I used to cart around one and I really hate it. Like, really, really hate it. Sorry, I've had a lot of issues with Bluetooth lately on this machine. So before I get into the implementation, another question is, what would happen if you have two condition variables that were not mutual exclusive? So less than 5 and less than 3. Well, I mean, you just have to be careful about using them. So for example, you know that if you have those conditions with like an if statement, if you put them in the wrong order, bad things are going to happen. So you just have to make sure that you put those in the right order. You'd have to use separate conditions. Really want to question too what your condition is. Like, does this actually make sense? I'm not saying it's not impossible, but you just got to be careful. So let's talk about condition variables. So let's talk about high level. What does CV wait do? So CV wait has to do a couple things. So first off, we need to fall asleep and release the lock. And if you look at the API for CV wait, it takes a CV and it also takes a lock. This lock here is the lock that we want to release. It is the lock we are using for mutual exclusion on the shared variable. Okay. So we want to fall asleep and release the lock. And then in this area here, we are asleep. And then at some point, somebody's going to call CV signal. So we're going to wake up here. And before we leave CV wait, we need to acquire the lock. And the lock we're trying to acquire is, again, this one, from up here. Because we want to make sure that when we enter CV wait, we own lock A. And when we leave CV wait, we own lock A. So when we call CV wait, it's as if we own the lock the whole time. even though we don't. Okay. So how are we going to actually do this? As I said, wishful thinking here. I thought the update to OneNote would actually fix the problem. Of course not. That would make life too easy. See, it erased everything on me. Yes, if you're wondering, I have actually tried some other pen writing apps, and I have not been happy. They either are super, super laggy or actually suffer from the same problem. But, yeah, we'll see what happens. So our condition variable takes a CV. That's the CV we want to fall asleep on, and it takes a lock, and that is the lock that protects the mutual that's giving us the mutual exclusion. So we should have some K assertions here. What kind of K asserts? Well, lock cannot be null. That would be really bad. And the CV cannot be null. That would also be really bad. Now, there's one other assertion that we want to do. We want to make sure that we own the lock. A lot of students say, well, when you call lock release, it's going to check for lock ownership anyways, so why bother calling it here? Here's the reason. The problem I have isn't in lock release. The problem I had is I'm in CV and I realized I didn't own the lock that was passed to me. So yes, calling it in lock release technically would make sure that the assertion failed. The problem is that when I called CV wait, I called it incorrectly. So we always want to make sure we throw the error at the exact point where we realize it, instead of passing it off and letting somebody else handle it. That way, when somebody is debugging their code, they will know the exact earliest moment at which the error was actually detected. So we do want to make sure in CV wait that we own the lock. For the comment on Twitch, good note and notability, they either don't have a free desktop version, or they also had issues with the tablet, unfortunately. And yeah, I'm not buying an iPad. I'm sorry, but this is probably going to be my last Apple product. All right. So, and for the people laughing at that comment, the reason is actually quite logical. Here's my issues. Every time Apple does an update, because they have not sufficiently abstracted their implementation of the kernel away from the user programs, or at least they make so many changes to security and libraries, half of the programs that I use on a daily basis break every single update. And I'm not talking about some kind of obscure program. I'm talking about OBS that I'm using right now to stream live to you. I'm talking about GIMP. I'm talking about GCC, like very basic programs, Zoom. All of every single time there's an update, all these programs have to be reinstalled and patched. That's really irritating. So that's problem number one. Problem number two is, despite being a BSD-based operating system, surprisingly using like basic new tools doesn't really work that well. So I would rather get a non-Apple and go back to normalcy. Well, if you do get a comment on Twitch, if you do get a co-op at Apple, good luck fixing that one. All right, anyways, that's not what we're talking about now. It's just, I appreciate that you were trying to help me with my problems with OneNote, but hopefully that won't be too long. So we've got our K assertions, and I hope you understand now why we want to check ownership of the lock here. It's because we want to make sure that the error gets thrown at the earliest possible point that we could detect it. Because if I detect it in lock release, I'm going to think there's a problem in lock release, not a problem in the CV. And the problem here is in the CV. It's not with lock release. It's the CV did something bad. You used the CV bad. Lock release did nothing wrong. It's just you passed CV wait something bad. So after you do all your appropriate lock assertions, we need to release our lock and fall asleep at the same time. And you know how to do this, because we did it in a semaphore and we did it in a lock, except instead of using a lock, we were using a spin lock. we don't need a spin lock in CV wait. So what we're going to do is we lock the wait channel. And then we call lock release. And then we go to sleep. See? It's the same pattern as before, the same consequences as before if you put them in the wrong order. But instead of using a spin lock, we are using this lock here. It's the same. And then after we sleep, we will wake up and we will acquire the lock again. There you go. That's not so hard. This CVs, honestly, so I don't ever remember implementing CVs in this course when I took it. Admittedly, I took this course about, it was over 15 years ago. But I don't ever actually remember us implementing these. And so I implemented the first time CVs when I first taught this course a few years ago. And I think they took me 2 minutes to implement because there's so little implementation to them. They're very, very simple. So then what goes into the signal and broadcast? Well, signal and broadcast, all they need to do is wake one or wake all. Now, if you actually look at the API that's posted in OS 161, you will notice that it says you have to own the lock that's passed to signal and broadcast. And that is a very long argument to have. For the purposes of this course, you do not need to own the lock in signal and broadcast. You must own it in wait, but you don't need to own it in signal and broadcast. I have kind of a guide as to why that is posted to Piazza, but to be quite frank, it doesn't even capture the whole picture. So part of the thing is the CV doesn't actually keep track of which lock it's been using the entire time. So technically you could call signal and broadcast with a completely different lock that's totally irrelevant, and it would work. So what's the point? The other issue is, even if you own the lock at the point of calling signal and broadcast, which you should, that doesn't mean that the thread that gets woken is going to be able to actually claim the condition. Because other threads might get to run before you do, and they may take the condition out from under you. They may make changes. So it doesn't really matter at the end of the day. So you should own the lock when you call signal and broadcast, but there's no reason to check. I mean, it's kind of on you. And this is one of those big arguments in the topic of OS and concurrency. A few of the other instructors are on one side and a few of us are on the other side. So for our purposes, we are saying that you do not need to own the locks in signal and broadcast, but you must hear and wait. All right. So that is all I want to talk about for today. In our next episode, we are going to look at volatile and other sources of race conditions, which have nothing to do with you, which is kind of exciting because you get to talk about compilers and CPUs and all those exciting things. Maybe that doesn't excite you, but I like talking about it. And then we're going to look at the last problem with synchronization. So we give you multiple threads and then you got race conditions. So we give you all these synchronization primitives to get rid of the race conditions, and now you get deadlocks. So how do you get rid of those? So that will be our next episode. And that will be on Thursday. And for those of you talking about how a lot of software who is on Twitch is going to have to change for Apple because of their M1 architecture, yes, you're absolutely right. And that's simply because the M1 obviously uses a different assembly language than the Intel chips and the AMD chips, which means that it's going to make compatibility much more complicated. That's just life. So the question is, could we have more coding examples? So that's a question on Twitch. And if you could respond right away, coding examples for what? So like what kind of coding samples are you looking for? Like P threads or just using condition variables? What are you looking for? I'll give you a moment to respond. So just more examples with multi-threading and p-threads. Okay, I will make a note and see what I can dig up. Admittedly, most of my own personal code base uses OpenMP, which isn't really helpful for you for this course. But I will see what I can dig up. I'm sure if I don't have anything, I'm sure some of my students might have something they'd be willing to share. So I'll see if I can get you guys some more code samples. Because obviously that's actually a really great way of learning and is from actually reading through code. I know, I think it was my second co-op position, I had to learn Fortran, and I didn't read a book. I just read through the code, and that's how people learn. So I'll see what I can find, but give me some time because it might take some time to dig that up. Either that, or I'm actually gonna have to write some p-threads code because I haven't written any in a long time. All right, so we will see you then next week or Thursday. I don't know what day it is.